Let us do this. How do I? There it is. How's everyone doing? Very good. Very good. Ándale. Dios mío. Unbelievable. What am I supposed to do? What am I supposed to do, huh? Now I'm good over here, right? All right, here we go. What are we looking at? Nebula. A nebula. So that's pretty good. That's a very good guess because we said nebulas are anything that is just cloudy.
Well,
But this is not a nebula. Yeah, the Eye of Sauron. Some people call it that.
Yeah.
What else could it be?
A lot of dust.
Wow.
A lot of dust. So dust is partially correct. You've already got one from my city. So dust is definitely partially correct. How is the dust oriented? Eye of the tiger. Incorrect. It's in a ring. It isn't a ring. It isn't a ring. Okay, so the star is right in the middle. But what I did is I covered it up. I didn't do this, obviously. So the star is covered up by something called a coronagraph, and it allows us to see the very faint dust that's right behind it. Okay? You can see all of these radiating spikes that are coming away from the main light there. So this is a planetary system that's forming. Can you find the planet?
Yeah.
If you can find the planet, you will win one of these.
Ooh.
Now, you already have one, so you can't win one.
Oh, can I still try it?
No.
Oh.
Because then you ruin someone's ability to get the lanyard.
Oh,
So this side has them. Only you can vote. Well, I think you have one. Where's the planet? You have one choice each, okay? No. Very, very reasonable, but incorrect. Nope. So, what are you giving up the answer?
I don't need the answer. It's just that like it's
No.
Oh.
This whole circle here?
Yeah.
No, that's a disc. It's a dust disc. Ooh, okay, now you're thinking with your head. Okay, that is not the planet I'm thinking of, but that's the right way to think about it. In fact, this is a planet, but it's not the one that I wanted. You gonna get it? Hopefully. Yes. See, there, and then that's yours. See? Well, the one that it's not literally belonging to. Oh. So this is Fomalhaut B. This system is the Fomalhaut system, and you stole the opportunities for anyone to get these fun things that I made.
They all try.
I'll try and fail, I guess. We'll have more
It
opportunities.
was a trick question.
It was a trick. No, it wasn't a trick question. Okay, so in fact, when we look out in the solar system, right, this is the whole planet, and look how many pixels we get on that. So many, so good. So in fact, you see a single pixel here. That's of course an exaggeration just due to the optics of the telescope. And what we have to do is we have to wait. And it's orbiting its parent star. So we watch it move all the way around. Cool, right?
So in 2 years it moved that far.
Yeah, but you don't know if that's far or close, right? I mean, the scales here, I didn't provide you any. So that's either big or small. Right? All right, so let's think about what we were talking about before. We were talking about building the planets. We already discussed orderly motions. We all fully understand how to do that, right? So that will certainly be on the homework. And you know how to answer those questions. And so we're talking now about building the planets. And we have two different groups and why they exist in the two different locations. So why is it that you have rocky planets close?
Because all the heavy stuff is nearest to the star.
And why is the heavy stuff? Why are the rocks near the star? Because what?
Hotter.
Hotter. Hotter. Does that make sense? Okay. So we look at the relative abundance by mass. We see that hydrogen and helium is the most abundant by mass, but it doesn't condense. It's really hard to make planets out of. So if I have only rocks and metals to make it with, then I have about 6% of the total material by mass. If I can grab any ices, 6%, sorry, 0.6% to 1.4%, it's a little more than double the material. So like a 200% increase. So if I took my paycheck, I had a 200% increase, I'd be pretty happy, right? Could do some more fun things with it. So if I can build with ice, I can make a pretty big house. The house being a metaphorical planet, okay? And that's the difference between the stuff that is close, warm, and far, cold. Okay, so inside the frost line, rocks and metals condense, but hydrogen compounds cannot condense. They do not become part of the planet. And you're asking yourself, well, this is a very tasty drink. Where did it come from? That's not comets. So comets delivered water and rocky asteroids delivered water. We'll see that at the end of today. Okay. So this is the first step to forming planets. First, you get stuff to stick together. Okay. And then, as I mentioned before, you get all this little tiny stuff to stick together. You smush it together very slowly. So when it's moving together, sticks. Okay. Things get bigger. They get bigger and they get bigger. They start to pull other things in. So now they have enough mass, they become circular. Those we call protoplanets, baby planets. Okay. And really small, really big ones, 10 times the size of the Earth, 20 times the mass of the Earth, they can grab hydrogen and helium. Hydrogen and helium doesn't have to condense. And it's a runaway process. So what does that mean? It means as you get bigger, you can grab more stuff. Right? So when we talked about what was the definition of a planet, we said there needed to be three things for something to be a planet. Spherical. Hold on, raise hands. You've won a lot of prizes. Okay.
You had to be spherical.
Okay, good. That's one.
You're.
Hold on, just one. I'm trying to give stuff away. You know what I'm saying?
You have to orbit the parent star.
Is to orbit the parent star, right? In this case, the sun. You've also won things. Yeah.
It has to clear its orbit.
Has to clear its orbit. That's the really important one here. So if you get large enough, you start to add stuff to your planet. Right? If you're big enough, you start swallowing up all of the nearby planetesimals. And they decide they want to be part of your house, so to speak. Okay. So objects that are past the frost line, they have a better chance of becoming big quicker. Okay. This fully explains the giant planets. And if I looked, if I could, it's like hydrogen, mostly hydrogen, small amount of rock and ice. Does that make sense? It makes sense because there's more hydrogen to start with. So even though I start off with something like 10 or 20 times the mass of the Earth in rocks and ice, I end up with Jupiter, which is like 300 times the mass of the Earth. So 280 of those is pure hydrogen and helium that are just sapped off, right? And so all of them have the same type of structure. And if you're very careful with your eyes, you'll notice that what is it, Uranus, Neptune? Neptune is slightly larger than Uranus. It's kind of weird. Big, smaller, smaller, bigger, and then Pluto. Okay, so how does this happen? It's something like this. You have the sun, all this gas that's falling in the sun, forming the sun itself. The sun then turns that into energy, as we'll talk about probably on Monday or one week. And meanwhile, you have a disk that forms around the sun. But the same exact thing happens around, say, proto-Jupiter. So Jupiter starts to accumulate material from the disk that falls in, and it creates a little disk of its own. And in the disk of its own, stuff that sticks together becomes the moons. So you have this little version of a solar system, but that one is going around Jupiter, or in the case of Saturn, that one is going around Saturn. Does that make sense? Questions about this? That's like all the planet formation we're gonna do, okay?
So this is how we figured out that something happened with impacts when there's a planet going the opposite direction of everything else.
Exactly, right. So something, if you see something unusual, right? So let's say all the planets form in a disk, right? And then let's say all the moons form in a disk. But now we see, let's say we look around Jupiter, and there's one that's going both backwards and totally inclined. So if the disk is like this, there's one going like that. So how did that happen? All right, so we have to have an explanation for that. In the same way that we needed an explanation for what the hell Pluto is doing. Because all the planets are in a disk like this, and Pluto's like this, right? Going back and forth, in and out of the disk. Okay, so let's hold on to that thought, because that's a good thought. Okay, so why are there only two types of planets? Well, that's the cosmic abundance of material in the first place. Okay. Temperature drops farther from the sun. Small stuff close, small planet are close. Outside the frost line, you have a lot of big stuff, and the big stuff can grab more stuff. Okay, rich get richer. Unavoidable, even in this. All right, so let's use this. Oh, shit. I don't want to have to use this material. Okay, so let's imagine a world. Okay, currently the distribution is 98% gas, 1.4% ice, and 0.6% rock and metal. But how would things look if there had been lots of rocks and metal, very little ice, and the same amount of gas? All right, let me know when you're ready. Show me those fists. Let's vote on 3, 2, 1. Okay, we got a few different camps here. Look around for someone who doesn't have your answer and see if you can convince them. You may have to move.
Yeah. And that one. That's what kind of collected. Yeah, I know. It's
All right. We good?
3 times the amount of metal in its ocean.
Okay, are you ready? Revote. Come to your fist when you're ready to revote. Vote on 3, 2, 1. Everybody's changing in so many different ways. Okay, so this will certainly be on your homework. So this is one of my favorite types of questions. How would the solar system look if it formed in very different conditions? Gets to use all of these different pieces that we've done so far. Right, so I can give you a fake solar system, can ask you to describe the planets, tell you there's a planet that's smaller. Oh God, now I have to think about week 4 when I learned about planetary processes, all this, right? Okay. So what is your thinking? Yeah,
So it says that rock and metal are both like basically 2% each, right? So like all of that material is gonna condense further in to make larger terrestrial planets.
okay.
Because like how the heat is gonna make it go towards like the inner circle of the sun. So that's where like there'll be more material for the terrestrial planets to grow larger.
Okay.
And because of that, there's not enough, like, there's not enough of that material to condense to form cores of large gas giants. So that's why I like even if gas is the same, there's not gonna be enough like pull from the rock, from like the rock and metals to create such large gassy giants.
Okay, so let me see if I can try and interpret that and you tell me if I got it right. You're thinking. You have some distribution of material, most of it is rock. So you have these massive terrestrial planets here, and then in the back, not really so much. Because there's not as much rock material.
Yeah, everything accumulated in like the inner disk, so there's not enough material to form gas giants like out back, so
Okay,
that's why I think that's it's for.
okay. I like some of the reasoning, but let's see if there are some other answers. Yeah,
Okay, so B and C are wrong. Because the gas giants can't form close, but they want to not, right?
the B and C are wrong because why?
Because it says, they both say gas giants close,
Okay,
but you need to be past the cross line in order to form a gas giant to begin with, right?
well, you tell me, I'm.
Well, it won't form because the hydrogen is too excited, it's not gonna want to condense. So.
Okay,
So it either has to be A or D, and then the hydrogen compounds have been reduced to 0.1% instead of 1.4%. So I don't think there's gonna be very many hydrogen planets. Or
Okay.
mostly hydrogen planets, so that's why I had gone with A.
A.
Yeah,
So you like large rocky planets close to the sun, maybe some icy planets, but no gas giants at all?
yeah, that's what I was.
Okay, so that's a 2 for no gas giants. Anyone like gas giants? They want them in the system? You like small gas giants? Which one was yours that you're thinking? Oh, you like them far away?
Yeah.
But you don't like them close. No one likes them close.
Up being small, rocky close, and then full stuff.
So let's think it's really important to think about what I'm saying here, right? Because the numbers matter, the temperatures matter, all of this matters. So let's go back one step. Okay. Okay, maybe it was 6 steps, fuck, I forget how far back it was. Alright, here it is. Alright. So the hydrogen and helium themselves never condense. Right? How does hydrogen and helium get into the planet? What's that?
The planet has to be 10 to 20 times the mass of Earth.
Okay, so you have to have enough mass before you can just draw it in on its own. Okay, so now let's look at these two here. Here's hydrogen compounds and rock and metal. What was the major difference between these? You talked about a frost line. What does that mean? What's a frost line mean?
Planets have started forming before in the sun at temperatures below 150 Kelvin.
Right, does it have to be 150 Kelvin? So it has to be 150 Kelvin for hydrogen compounds. What about for rock? So there's this weird like rock condensation line. You would never call it a frost line, right? But what if all you had is rock? In our example, 1.9% of the material is only rock, and there's very little hydrogen. So that is condensed almost right up to the star. And the amount is as much as the isotopes. And it's condensed right up to the star. Do we see it yet?
So we don't have that.
We will have gas giants close because there's plenty of material and it condenses right away. It doesn't need the frost. So the reason why the frost line matters for us is because most of our material is in hydrogen compounds, right? An annoying question? Yeah. Yeah. Hated it. Okay, good. All right, let's keep going. We're gonna have other examples, I promise. We'll play with this idea a lot. But when we build these systems, it's important to think about the way that these two different things work with one another. Condensation temperature, right? Just because we think of them as important for us doesn't mean that they're always important, right? Okay, shit, this is a lot of where to go. Okay. So in fact, gas giants with rock metal cores will be close. And gas giants with rock metal ice cores will be fun. Okay. We did it, yeah. Okay, so let's figure out this next one. Why are there two types of small bodies? And I'll give you a hint. Has to do with the fact that it's hot and cold. So we don't have comets close, except for when they're on their way on a suicide mission, right? And we don't have a lot of asteroids far. We do, but you'll find out why they're so far up there. It's very unusual. Okay. Okay. So now we've formed the planets. Okay. We're imagining a world in which we have all of our big planets and we have a bunch of stuff left over. We have gas, the stuff that you make the gas giants with, the stuff that you made the star with, and you have junk, right? And this is the dust, the small planetesimals, the rock bits, everything like that from the formation of the solar system. So what happens to the gas? It goes away. Why does it go away?
University.
Close. We saw pictures of this, remember?
Solar.
Solar wind, star hot, star blow, star cleanup gas. Okay, that's exactly what happens. So just like we saw these pictures before, right? These like beautiful nebula, and you have a little dot in the middle, and it's like great structure. Maybe it looks like it's got cobwebs all over it. That's literally what's happening here. But we're way zoomed in. Okay, that's half a light here. It's an absurd distance when you consider it. Okay, so here's a hot massive star. And this is a small star nearby, a friend, and he's blowing off this one's disk. He's so hot, he's like literally incinerating the other disk. Okay? And this happens on a time scale of I think hundreds of millions of years. So after you start to form the planets, you have a short window to grab as much stuff as you can before the gas is gone forever. Okay? Solid stuff, it's not worried. So planets, moons, asteroids, comets, they don't get blown away by the solar wind. Okay. But let's look at the remainder. So we saw, for example, asteroids are the leftover pieces of rock. Okay. And comets are the leftover pieces of ice. Pretty straightforward, right? Okay. You get these two distributions. You have stuff that's sort of like in a plane. And then you have this cloud stuff. So these are all flung out in really random directions. You might be saying to yourself, huh, that doesn't make any sense, Krismani. You said everything was orbiting the same direction. So now we have another thing we have to explain. So far we have to explain why we have moons going in random directions. Now we have to explain why these comets go in random directions. We'll note that asteroids do not do this. Asteroids do not go in random directions, and they don't ever go like this out of the plane and back in again. Comets have no problem doing this. Okay. And then you have the normal boys, right? You have your Kuiper belt objects. Those come along. They like sometimes hit Jupiter, sometimes hit us. They hit us and they cause dinosaur times mass extinction. But not very frequent, just sometimes. Okay, so let's ask another question. What would have happened if the solar wind had turned on earlier, still after condensation and accretion of planets? A, the planets would all have thicker atmospheres. B, Jovian planets would not be as large. C, terrestrial planets would not be as large. D, Earth's moon would look different. E, there'd be a lot more comets and asteroids. So when you're ready, vote on 3, 2, 1. Okay, we got two different camps here essentially. And then we want to support the argument. Yeah.
Well, if the solar wind had turned on much earlier, it would have blown away more of the gas,
Okay.
therefore leaving the Jovian planets not to have as much to go with.
So you like B. Anyone disagree with that? Well, is he right or not? Did he convince you if you had a different answer? Yes, he did. So in fact, that's exactly what would happen. Jovian planets, because they grab their gas from the disk, they have a limited amount of time to do this. So if you have a more excitable star, so to say, with stronger solar wind, it'll get rid of that gas more quickly. And we saw that happening in the picture of this massive star blowing away the smaller star's disk. So that smaller star is very unlikely to have big, giant planets, right? The massive star also unlikely to have massive planets. Okay. We did it! That one was quick. Questions about this part? Okay, so now let's do the exceptions to the rule. So which of the characteristics Record scratch. Which characteristics of Earth is not yet explained by our formation theory so far? So far, here's the things we have in our book, right? We say that the nebula collapses. As it collapses, it spins, it heats up, and becomes a disk. And then there's condensation. So even though it was hot, it cools down, rocks cool out of it, ice cools out of it. That becomes the building blocks for planets. That accretes into these little protoplanets or planetesimals. When they're big, they can grab gas. And then eventually, the solar wind gets intense enough that it removes all the gas that's left. And all you have is planetesimals and giant planets, asteroids and comets and stuff. Okay, so is it A, Earth is composed of rocks and metals, B, Earth has oceans, C, Earth orbits the sun counterclockwise, D, Earth has very little hydrogen and helium, E, Earth is located in the inner solar system. So which of these is not, is not explained by what we've talked about. Let's vote. Vote on 3, 2, 1. Okay, I think a lot of people got it. All right, anyone want to defend their answer? Yeah,
So I don't know if that motion,
why is that?
because, why didn't Mars have a? It was formed the same.
Why doesn't Mars have oceans? Yeah, okay, so your argument is that
Nearby planets.
this one I haven't heard anything about.
Yeah.
Okay. All right, another way you could do that is if you said, well, okay, I've heard about
It's
this.
the same stuff.
Yeah, made of the same stuff, okay. And so Earth is located in the inner solar system, that's explained by what?
Close to the sun where the material galaxies.
Exactly, right? So this is explained by condensation and accretion. The fact that it has little hydrogen and helium, same. What about this one? Earth orbits the sun counterclockwise. Nebular collapse, right? That's the first one. Earth is composed of rocks and metal. Well, that's kind of like the same as these ones, right? We haven't talked about the ocean. Let's see. Okay. So after the planets formed, there's still material left over. This is probably what Earth looked like. Boring, right? Oh, she's not cute. She's like boring. Look, it's like it's got a little, it's like not even cantaloupe. It's like gross. There's like warm cantaloupe on the inside. Ugh. Thin skin, and it keeps getting hit. It keeps getting hit. There's like lava on the surface. Maybe there's a little atmosphere. It's very boring. Okay. There's no rivers. There's no green. Okay. So this period, right after the planets formed, it's just stuff flying around. And you can see on the moon, the oldest places on the moon have huge regions of crater on crater on crater on crater on crater. And we'll do this when we talk about asteroids on Monday in the lab. And also you'll see this when we look at the moon, if we ever get an opportunity to observe it. Eventually, maybe not till next year. Okay, and we described, for example, collisions can explain a lot of the things that we've described so far. They explain all those. Did those all make sense? Even though I didn't say anything. Okay, how did it happen? So essentially, what people think. Here, I'm only showing you the giant planets. This one here is Jupiter, Saturn, Neptune, and Uranus. And you'll notice I said them wrong. Jupiter, Saturn, Neptune, and Uranus. Okay. And they probably all formed actually quite close to one another. And all of these green dots, these are going to be your icy leftovers. So these are our Kuiper belt objects. And they start in a very nice, tightly knit configuration. But because everyone starts really close to one another, they start pulling on each other gravitationally. And you get a little bit of wobbling in the orbits. Some of them get too close to the resonant lines we talked about. In particular, when Saturn gets to a position where it goes around twice, or sorry, it goes around once for every time Jupiter goes around, then things go haywire. And you have a crossing of the resonance, which lets the whole thing go completely out of whack. Uranus and Neptune likely switch places, and they all get flung out much farther than they would have been earlier. All of this material gets spread out. Some of it gets flung out into the Oort cloud. Some of it gets flung directly into the planets. And this is, go ahead.
Is that kind of like, is that also a theory of how the heavy bombardment period started? Because
This is,
Neptune was flown.
yeah, this is what I'm showing you right here. So this is the exact time when this is happening. Exactly right. So when we think about this happening in sort of a very short time frame, right, from 880 to 833, there's like 3 million years when everything goes haywire, just like you're thinking, right? So it's a very discrete time period. Suddenly everything exploded. By the time that it's about 1.2 billion years into the solar system's history, everything's calmed down. And that's good. Because when we talk about life, Takes like 2 billion years for life to even do anything interesting. You get monoculture or monocellular life really quickly, and then it's really boring for a long time. Okay. Okay, so just as you mentioned, this is probably the cause for the late heavy bombardment. It also explains why you have all these captured satellites. So when you look at Phobos and Deimos, these are the moons of Mars, and they just look like asteroids. And they look like asteroids because they're probably asteroids, right? They are what they look like. They're unlikely to have formed in a disk around Mars. They're unlikely to have formed like the moon did not form in a disk around us. There's no evidence of that at all. These are all collisionally created objects. And it also explains why they just orbit however they want, right? These two do not orbit in a plane with one another. They orbit like this, right? Okay. Questions? Okay, well, we did it. That's the whole thing. Now we understand the nebular theory of planetary formation. And when you go home tonight, you can obviously tell your mom, as you always do, call her on the drive home. Hey, I found out how planets are formed. Okay. Uh-oh. That seems like a lot of words. So which of the following observations would be inconsistent with our current theory of the solar system formation? A, we discover a new small moon of Uranus orbiting clockwise as viewed from above. B, we discover a previously unknown large comet passing through the inner solar system. C, we discover another solar system with 6 planets, all of which are Jovian and closer to their relatively cool star than our Earth is to the sun. D, we discover a rocky dwarf planet beyond the orbit of Pluto with an orbit that is nearly circular in the same plane as the Jovian planets. E, we discover a small object orbiting the sun with the same semi-major axis as Jupiter, but with density similar to the asteroids. Let me know when you're ready to vote. Vote on 3, 2, 1. Okay, I think I got every answer. That was pretty fun. You want to ask your friend what they think? You can make a new friend too. Your friend has the same answer. And go across the aisle. Did you do any of those lights actually?
I was like, I don't know.
Yeah.
Are you ready to revote? You're gonna tell us what you got? Yes. No. Okay. I'm just saying generally, I feel like getting hyped to talk, like she's up next, All right, let's vote. Let me know when you're ready. On 3, 2, 1. That's too many. You can't have both choices. that you can't blink through them either. All right, does anyone want to support their argument? The last stick of the day, yeah.
Well, if it's beyond Pluto and Pluto's not a planet, then the rest are not planets.
But I said dwarf planet.
I don't.
That's a good one. I like that one. So the nice thing about this is a very opaque set of answers. Okay. Oh my glob. And I chose all of these. What? I chose all of these because they all actually exist.
Wow.
But the question is whether or not they fit into our current understanding of the nebular theory. Okay. So this one here happened last year. The first one.
Mhm.
We were just looking at Uranus, we're like, there's another fucking moon. It's crazy. Every time you look, there's a new moon. It's far away, it's hard to see, they're dark, right? And they're small. And it doesn't even matter if it was orbiting clockwise or counterclockwise. Why?
It could have been captured.
It could have been captured, right? Just like we know all these weird ones can get captured. So this is perfectly fine. We accept that. What about this one down here? A small object orbiting the sun with the same semi-major axis as Jupiter, but density similar to the known asteroids.
That wouldn't happen, right, because it would have to clear its orbit.
Well, this one's a little tricky. This one also already exists. I told you all of them exist, right?
Yeah.
Oh. These are the Trojans. These are the Trojan and the Greek asteroids. They orbit in front and behind Jupiter. They did not form there. They were captured. They were asteroids that formed in the asteroid belts and then got captured during the migration. But this one's fine.
But they're just hanging out.
Yeah, they're just living their best lives.
Not
They're just
cool.
rocks. They're just like rock, and this is why they have the same density as asteroids, because they are asteroids.
But they don't move.
They move with Jupiter. So in Jupiter's reference frame, right? Imagine that I'm Jupiter, I'm going around like this. Now let's hold it like this. They'll just sit right here and right here. Yeah, it's very fun.
Really?
Yeah.
They just don't.
Yeah, it's here and here.
That's like.
There's a few places in the solar system. They're called equipotential places. And what this means is I'm the sun and I'm the Earth, or let's say I'm the sun, and I'm Jupiter, whatever you have, so big object. There will be a place in between the two where the forces balance. There's one here, there's one on the opposite side, and there's two to the side here, there's one on the all the way down.
Is they're captured, but they're not cool?
It's lived that way.
So they were just going by, oh, you caught me, I'm just gonna stay here.
Well, usually it's a little trickier. They get roped into that area. They make little circles around their location, but they just go.
That's what JWST is doing, right?
Yes, JWST is at L2. So if this is the sun, the Earth, JWST is right here on the backside. These would be in the places L4 or L3 and L4. 1, 2, 3, 4, 5. And if you like that, you take Astro 3300 going all about it. Oh no. Oh no. Okay, so we did that one. We did that one. What about this one?
It just could come from lower part.
Yeah, it just come from any time. That happened. This is what I did my PhD on. It happened last year, interstellar visitor, right? But it really was an asteroid. It really was a comet. What's that? What about this one? This one okay? Yeah, we're looking for one. There's a whole group of scientists. I don't personally believe it, but there's a whole group of scientists who think that there's a rocky planet out past Pluto and Planet X. Yeah, that's exactly right. And they're looking for this planet because it would explain why a lot of the Kuiper Belt objects are distributed in space the way that they are. If they were getting pulled by a massive object out there.
Why do you believe it?
Because I don't like this.
Maybe that's
I think so. There's a difference between what we think of as like an observational bias. When you look in a certain region and you see something compared to understanding the entire area. And they don't have a full picture yet. So they're making a presumption based on inadequate data, in my opinion.
Well, what if we hit Pluto and that's what made this orbit?
Well, we think probably Charon hit Pluto. Right, I mean, there's definitely lots of little planets in there too. When we were arriving at Pluto, we found 3 more moons. So they were like, oh shit, there's a lot of stuff around here. What about this one? So this one is the answer that I wanted you to come to. We don't have it yet here. We don't quite have an explanation of how this could happen. 6 Jovian planets closer than the Earth. That makes sense.
But it says that there's stars killer.
Right, yeah, so it says cooler. That's where there's a little wiggle room here, right? So I let there be a little wiggle room, so I let other answers be okay here. So the nice thing about this one is that because they're cooler, you could say, well, maybe the ice condenses much closer. But think about relatively cool. It's any star, right? Think about Mercury, for example. You get to Mercury's distance, or you get to our distance. You throw ice out of a spaceship, it's gonna melt at Earth's distance. So you drop it by 100 times as bright. It's still gonna melt. It's a very big star, right? So there's some wiggle room here. But in fact, we have seen this. 6 massive Jupiter-sized planets, all packed in between where we traditionally think of as the Earth and the edge of their star. We've seen some that are so close that they're like basically almost touching. They're like sharing a surface. So the question is, how does that happen? That's the one.
Going outside and looking at that.
Well, yeah, and when we talk about exoplanets, it's really cool because everything that you can think of probably already exists. Tatooine, real planetary system with 2 stars. No,
No, that's cool.
no, we're not going. Why not? No. Well, that's the ethics of space colonization. We'll talk about that later. Okay, so if you think about this, you can really understand most of the scenarios. So imagine I put this on the homework. How would the planets in the solar system look if the nebula had been cleared away before the capture of any nebular gas? No gas giants. Bingo. Now you got it, right? Trickier one. How would the solar system look if ice is condensed at 50 degrees rather than 150 degrees? More icy planets? More comets?
Would like other planets have water too?
Other planets have water? Let's read this carefully. How would the solar system look if ice is condensed at 50 instead of 150? Is this hotter or colder? Colder. So is that closer or farther to the sun? Farther. So this moves the frost line away from the sun, not closer. So do you have more or less gas giants? Less. Do you have more or less asteroids that are icy? Less. Do you have more or less comets? Less. Counterintuitive with the condensation temperature there, right? You think cold, you think better. No, it's worse. Okay, what about this one? Okay, how would planets in our solar system be different if the whole solar nebula had cooled below the condensation temperature of hydrogen compounds, 150, before solar wind clearance? More gas giants? Any terrestrial planets? No. No? No. No?
If you're still gonna, there's still that rock though, then.
Yeah, good question. What happens to the terrestrial planets in this circumstance? Say that again, please. Well, so this is saying the solar nebula cools down before the gas gets cleared. And my question is whether or not there are terrestrial planets at all. they would collect hydrogen too. So there would be terrestrial planets, but underneath an envelope or a gas giant's body, right? So there wouldn't be any terrestrial planets because they would be the cores of all of the gas giants that now exist. Okay? So now you can understand everything about the solar system formation. Cool, right? No one thinks so. That's
Wow,
fine.
so cool.
Okay, so when did this all happen? A minute ago. When did this class start? That was about the same time. Okay, so how old is the solar system? Is it about 13.7 billion years old? 4.6 billion years old, 250 million years old, 5 million years old, and we cannot, I should put the 6,000 right here. Just for those folks. 20? That's because when you were born? Oh my gosh. All right. Let me know. Let me know when you're ready to vote by showing me your fist. Let's vote on 3, 2, 1. Okay, I got all 1s and 2s.
Question, what do you mean call the source, like when they start forming or like once the planets form?
Is that the same answer?
I don't think so.
How different is that answer? How many billions of years, how many millions of years, how many tens of years did it take for the gas cloud to collapse to make the planets? Any idea?
In like between A and B.
You think in between here?
Yeah,
Okay, you think like the gas cloud started collapsing like right here,
yes.
and then you made planets here?
Yeah.
Okay. What is this number, folks? That's the age of the whole universe.
Oh,
So you do recognize this number, but it's a different number. So there's no time before that time. That's when the initial clocks start running. Okay. This one here is the age of the solar system. And you don't know this yet, but we'll see that the formation happens quite quickly. Millions of years, but in a geologic, cosmological time sense, it's like this. Right? And I'll show you more. So how the hell do we know it? We can see stuff. We have rock bits. And these meteorites are really cool. So they have inclusions. If you look here, that's an inclusion. These are called inclusions. And you have these little spherical ones. These are calcium aluminum inclusions. And this is material that condensed from the nebular disk. This material never was part of a planet. I'll repeat. This is the dust. When people were asking me, well, what's the dust, Matteo? That's the dust. Some of it's calcium, some of it's aluminum, just atoms hanging out. And then it gets into this disk and it cools down enough that it forms these little balls, magma balls of calcium and aluminum. And what we can do is we can do isotopic testing and we find out exactly how old it is. And it's been dated at 4.567 billion years old. The oldest thing that we have ever found in the solar system. Now, youngest things are found all the time. That's not surprising. There's 0 things that we've ever found older than this date.
That's one of the old stuff.
Yeah, this is the leftover stuff, right? And you might think, well, why not just look on Earth and just grab some good old Earth stuff, right? Why is that? Why can't you just grab old Earth stuff? Too new, it's been recycled,
Yeah.
right? The rock stuff has been recycled. We even got hit by the moon. The oldest stuff that we could ever possibly find on Earth can't be older than when we got hit by the moon, right? Because those rocks reformed. So the only stuff we can use, well, that's not true. The best stuff we can use is the stuff that's left over from formation. Okay. They also contain an isotope of iron that forms in exploding stars. We'll talk about that very briefly. It's called nucleosynthesis. But we think possibly the reason that our solar system formed in the first place is a nearby supernova went off, seeded our gas cloud, and the gas cloud collapsed. Cool, right? People familiar with the idea of radioactivity? Okay, let's describe it really quick. We're gonna do a class demonstration. I need everyone to stand up. Okay. So I don't have a clicker. I should have changed this. The first question, are you standing up? No, Caesar's not standing up. Come on. Okay, so we're all gonna pretend that we are one of two types of atoms. Okay, you're either going to be, let's choose argon and potassium. So right now, if you're standing, you are argon. And if you sit down, you become potassium. Sorry, other way around. Potassium and argon, okay? What, you can't sit already? Okay, so what we're gonna do is we're gonna close our eyes, okay? And then I'll say 1, 2, 3, and some number of you will randomly choose to sit down. Okay, and then we'll open our eyes, we'll see how many are left, and we'll do it again and again. Don't all do it at the same time. I know what you're thinking. Don't you dare. Okay, so close your eyes. Let's sit on 3, 2, 1. Okay, and now open your eyes. Okay. So right now, 1, 2, 3, 4, 5 of how many were there originally? Like 15? So about a third. Okay. So now close your eyes again. 1, 2, 3. Okay, open your eyes. Now 1, 2, 3, 4, 5 of 13, 14, 15, right? So now about half of you have sit down. Took only 2 times for half of you to sit down. Let's try it again. Close your eyes. 3, 2, 1. Okay, open your eyes. You can't stand up again. You can't transition back. Okay, now 4 of you are standing. It's less. Try one more time. Close your eyes. 3, 2, 1. Oh, interesting. All right, so now 3 of you. So at the end, maybe it goes more slowly. It's no longer uniform. Now you don't want to sit down at all, but you're welcome to sit down. Okay. So this process essentially is something called a half-life. Okay. So the half-life of the students, we're going to ignore some of these words, but essentially what we're doing is at time 0, all the students were standing, and after 2 sort of opens and closes, half of them were standing. Right? So what that means is that you start with a potassium amount up here, and after about 2 sits, half of them have turned into argon. That's the sitting people, right? And the distribution of potassium can only go down. You can only sit down, even if you're Caesar and you want to stand back up again. Okay? Because potassium goes into argon. They are the same type of element. One of them decays into the other. And this is how we tell how old things are. So if we look at the ratio of these 2 to one another, they tell us how many billions of years it's been since the rock turned into a rock. Will this work on gases? No. You got to trap the things in there. You can let new gas in and old gas out, then it's not a very reliable metric. Now, if you can trap the gas in a little circle, you can do that. That's okay. So in fact, we can do this to water in a really fun way when we see the hydrated water inside of Martian meteorites. What? There are pieces of Mars that have smashed, right? Impact. They come off of Mars, they go into space. And then they fall to Earth. And we pick them up and we say, huh, you look like Mars. In fact, the most accurate evidence that we have of ancient Mars is from Martian meteorites from 4.6 billion years ago. Pretty present, right? Pretty cool. Okay, so this is how we do it. It's called radioactive decay. Does this process make sense? Because we're going to ask a quicker question about it. You're all ready to discuss it? You're all ready to see it on the homework? You have no questions about it? All right. Suppose you analyze the radioactive isotopes in a meteorite and discover there's 3 times as much argon-40 as potassium-40. How old is the rock? Remember that potassium-40 decays into argon-40 with a half-life of 1.25 billion years. And I'll let you do the math here. Do you need the picture? You want the words or the picture? Which do you prefer? Are you ready to vote? No. Still doing the math. Okay, do the math. Figure it out, figure it out. We go back one. Picture now. Here's the picture. All right, ready to vote? Vote on 3, 2, 1. Yeah. P and D. Divided by or?
Oh, sorry.
I really like this. Want to explain the answer? Yeah. Let's go to the picture.
Okay, so there was 3 times as much argon as potassium.
3 times as much argon as potassium. Okay, so where's my
Right there.
right here?
To half-life mark, which is 1.25 times 2 billion years. There's 0.25 of the units, fractions of potassium, and if you go straight up to potassium, that's about 1.75, which is 3 times.
Right. So this amount here is 0.25. And then I put it up here. So it's 75% and 25%. One is 3 times the other. So I find this number here. 2 half-lives. And how old is that?
2.5.
2.5 billion years. That's all rock. Right? This is also why you never eat bananas, right? Disgusting things give you radioactivity. I'm just kidding. I mean, actually, I don't like bananas, but that's not because of the radioactivity. It's just because they're gross. So if you think about how long this is radioactive for, this, if you remember your quantum mechanics, which you may have not have taken yet, but you'll find out later. The length of the time scale here is also talking about how energetic it is. Not a very energetic transition. No side bananas are safe to eat. All right. So here's the math. Let's not do the derivation. You can do that at 1 if you want. It's just a logarithm. Okay, t over t to the half. And it's a doubling. So every time that you hit a half-life, you divide by 2. Straightforward, right? Okay. So what do we look at to date the age of the solar system? Earth? You don't like it. Anyone like the Earth? Earth haters. Okay, what about the moon? No one likes the moon. Moon formed after. Earth formed after. Solar system bodies, small ones. They're the remnants, right? We already talked about asteroids as being leftover junk. Turns out it's not useless. Right? The oldest solar system rocks are about 4.4 billion years old here on Earth. They're found in Australia. Australia is the oldest continental crust in the world. And there are places where you find these things called zircons. They're super, super old. The oldest moon rocks are between 4.4 and 4.5 billion years old. That's a person. Little baby person, big rock. No stars. Oh, why no stars?
Green screen.
Green screen, wrong answer. What did you say about the camera?
It's something about the shutter thing with the camera that's focused on the whiteness of the moon, so you can't
Exactly.
get the background.
This is bright, so you can't see the background. Just like you have on your phone, gets blown out by something that's near, you won't see the dark details in the back. So in order to do this well, you need high dynamic resolution, and these were film cameras from 1960s. Okay, you've ever seen what we call like a Polaroid? Let's imagine that, but worse. Okay. Meteorites, however, date back even farther, between 4.53 and 4.58 billion years old. So, of course, the Holy Grail, what everyone is looking for, is the meteorite that comes from outside our solar system. It's certain probably exists. And in fact, people have done calculations. They look at meteorites from outside of the solar system. They say if you just like go onto the moon, because the moon's relatively pristine, it hasn't had any weathering, it hasn't had any like erosion or anything, and you go up there with a big like sifter to look for a meteorite from another solar system, and you probably will find like 10. Pretty good odds. Okay, so the oldest rocks we've ever found, in fact, we think the oldest part of our solar system is about 4.55 billion years to about 1% accuracy. So to your point, you're saying, well, how quickly does this happen? So the rocks probably form around this time. And crazily enough, it takes like 100 million years for the planets to fully form, for them to get hit by their new moon, for them to accumulate all that gas and dust. It's really, really quick. And that's maybe not as surprising when you think about how quickly the moon formed after hitting us. I showed you the simulations that are relatively new, last 3 years, that show that the moon formed in basically a matter of hours. You smash into stuff, and you form a new moon right off. You upset about that? Okay. All right. So let's think about the stages of solar system formation, and then we'll be ready. We'll be done. Okay. What's the first stage? Nebula collapse. Very good. Does this work? Did I do it right? Let's go. Okay, then what? Close right before that? Condensation, right? We got to make sure that we have stuff to stick together, right? So that's condensation. And this becomes the seeds, right? So you have this like warm rock here, and then you have cold seeds out here. And then? Okay, accretion, got the right answer already. And is there anything else about accretion? You have accretion, which is small things sticking together, and if you're big enough, gas capture, right? So you get both. So now you get terrestrial planets close and gas giants far. And that's moderated by how hot it is compared to the nearby line. And then are you done? No. Clearing what?
Leftover gas.
Clearing out leftover gas. Okay, solar wind clearing. And in the solar wind clearing, you probably have some stuff move around a little bit. You get rid of any of the extra junk, smash it into planets if you don't want it, whatever. Okay, that's the happy ball. Ta-da! Any other questions, comments, concerns? Okay, so I'll post the homework tonight, and we will do. So here's the question. We're running out of time. Do we want to spend one class on exoplanets, or do you want to say fuck them planets and let's go on to stars? Raise your hands for planets. Raise your hand for stars. You can raise them for both if you want to. I think stars win. Let's do that again. Stars 3, 4, 5, 6 planets. 2, 4, 6. Ooh. That's as close as it could be. I'm the tiebreaker? Caesar, what do you want to learn more about? He wasn't listening. Stars. Okay, you want stars. So here's the thing about stars. When we got into stars, the pictures would be less cool at first. The ideas are great. So how do you get carbon? What happens to a star when it dies? What's a black hole? We'll do all those things. How do supernova happen? And I might do like 5 seconds at the beginning to show you maybe 3 or 4 of my favorite exoplanets. But maybe we just investigate those in the homework. I'll give you some examples of real planets, and you'll tell me what you think happened. That sound good? Okay, please bring your homework up here and look for that to be posted either later tonight or tomorrow.